To human eyes, the night sky is a silent canvas of black velvet, punctured by white pinpoints of light. But the universe does not speak in the narrow band of visible radiation. The true history of cosmic time, from the primordial expansion of the Big Bang to the frozen reservoirs of prebiotic chemistry, is encoded in infrared light. On March 11, 2025, a SpaceX Falcon 9 ignited against the night sky at Vandenberg Space Force Base, carrying an observatory designed to fundamentally change how humanity sees the cosmos, NASA's SPHEREx. SPHEREx was not built to focus on a single distant galaxy or stare down a single exoplanet. Instead, it was engineered to perform a breathtaking feat, mapping every single coordinate of the entire celestial sphere in 102 distinct colors of infrared light. Operating an infrared observatory requires overcoming a relentless enemy: heat. Every warm object, including the Earth, the Moon, and the Sun, glows brightly in infrared, threatening to blind sensitive astronomical detectors. SPHEREx executes a brilliant orbital choreography to survive. Flying in low Earth orbit, the spacecraft rides directly along Earth's Terminator, the perpetual dividing line between day and night. This unique geometry keeps its solar panels continuously illuminated for uninterrupted electrical power, while allowing its conical white sun shields to deflect incoming thermal radiation. Deep inside these nested shields, the optics remain passively chilled to cryogenic temperatures without consumable liquid coolant. Using automated planning algorithms developed at Arizona State University, the spacecraft maneuvers strictly within an orbit-varying allowable pointing zone, taking exposures and slewing systematically across the sky. Traditional space telescopes rely on motorized filter wheels or complex slit spectrometers to break light into spectra, limiting their field of view. SPHEREx achieves full sky spectroscopy through an elegant, solid-state optical design. Its focal plane is equipped with 6 specialized detector chips mounted with linear variable filters. As light falls across each chip, different physical regions filter out specific wavelengths of infrared light. Rather than taking a single, static photograph, the spacecraft observes a patch of sky, records the spectral data, and then steps across the sky in interlocking mosaic tiles. Over 7 months of continuous scanning, every single pixel on the celestial sphere is revisited at least 102 times, once for every unique infrared color band. Over its primary 25-month mission, SPHEREx will produce 4 complete, independent, all-sky spectral atlases. Between May and December 2025, SPHEREx completed its maiden sweep across the heavens, returning a dual-perspective, all-sky mosaic that fundamentally transforms our perception of the Milky Way. The first mosaic isolates the diffuse interstellar medium, the celestial tapestry of gas and dust from which future stars and solar systems are born. Stretching horizontally across the core of the image is the dense plane of our galaxy, glowing in 2 carefully isolated infrared wavelengths. The prominent crimson clouds wrapping through the galactic disk are polycyclic aromatic hydrocarbons, or PAHs. These complex, carbon-rich ring molecules emit intensely at 3.4 microns when excited by starlight. PAHs represent the primordial soot of dying stars, forged in the outer envelopes of red giants and dispersed across interstellar space over millions of years to seed the interstellar clouds of our galaxy. Interspersed among the dense crimson dust clouds are vast, glowing blue bubbles of hot hydrogen gas, radiating at 4.0 microns. These luminous cavities mark active stellar nurseries, where clusters of massive, newborn stars have ignited. Their intense ultraviolet radiation and powerful stellar winds ionize surrounding hydrogen gas, carving colossal hollows into the interstellar medium and compressing adjacent gas into new generations of stars. Breaking down starlight into individual wavelengths, a technique known as spectroscopy, allows SPHEREx to map the large-scale distribution of these elemental building blocks across the entire Milky Way, measuring the precise energetic feedback that governs galactic evolution. Beyond glowing gas and dust, SPHEREx's all-sky spectroscopic capability unlocks an astrobiological treasure, reading absorption signatures inside cold, dense molecular clouds. As infrared starlight passes through these dark nurseries, frozen molecules on dust grains absorb specific wavelengths, leaving distinct chemical barcodes in the spectrum. SPHEREx systematically charts the galactic abundance of three vital biogenic ices: water ice, carbon dioxide ice, and carbon monoxide ice. These frozen volatiles are the foundational reservoirs of prebiotic organic chemistry and the primary source of water in planetary systems. By mapping these ices across the entire galaxy, astronomers can trace how the essential ingredients for habitability travel from interstellar space into collapsing protoplanetary disks, asteroids, and infant worlds. Shifting to its second all-sky mosaic, SPHEREx turns its gaze from the interstellar dust of our galaxy to the stellar architecture of the broader cosmos. In this visualization, short, medium, and long infrared wavelengths are rendered in blue, green, and red. The central Milky Way blazes with the light of billions of individual stars, while the vast fields above and below the galactic plane are populated by hundreds of millions of external galaxies. Because SPHEREx observes in 102 distinct colors, it functions as a cosmological distance engine. By measuring how the characteristic light of each galaxy is stretched toward longer, redder wavelengths by the expansion of space-time, SPHEREx determines the precise spectroscopic redshift for hundreds of millions of galaxies, transforming a two-dimensional sky map into a massive, three-dimensional atlas of the universe. This vast three-dimensional cosmic web holds the key to the ultimate origin question: what occurred in the first split second of creation? In the first billionth of a trillionth of a trillionth of a second after the Big Bang, the universe underwent an epoch of exponential expansion known as cosmic inflation. During this instant, subatomic quantum fluctuations in the fabric of spacetime were stretched across cosmological scales, freezing into subtle primordial density ripples. Over billions of years, gravity pulled matter into these dense regions, giving birth to the first stars, galaxies, and colossal cosmic filaments. By analyzing the large-scale statistical distribution of hundreds of millions of galaxies across cosmic time, SPHEREx provides direct empirical constraints on the physics of inflation, testing whether primordial fluctuations were driven by a single quantum field or more complex cosmological mechanisms. SPHEREx's journey to orbit was shared with another pioneering NASA explorer. Encapsulated inside the payload fairing of the SpaceX Falcon 9 rocket was the PUNCH mission, the polarimeter to unify the corona and heliosphere. Composed of 4 synchronized orbital satellites, PUNCH is dedicated to observing the outer atmosphere of the Sun, tracking the critical transition zone where the hot solar corona accelerates into the supersonic solar wind that sweeps across interplanetary space. By combining wide-field polarization imaging with real-time tracking of coronal mass ejections, PUNCH monitors space weather from the Sun's surface to Earth's orbit. The co-manifested launch of SPHEREx and PUNCH demonstrates a new paradigm of multi-mission efficiency, deploying world-class astrophysics and heliophysics observatories on a single launch vehicle. Operating along Earth's Terminator line, SPHEREx stands as an essential component of NASA's distributed fleet of active scientific spacecraft. Across our solar system, an interconnected network of robotic sentinels surveys the cosmos. In low Earth orbit, Earth-observing platforms like SWOT and PACE monitor our biosphere alongside orbital observatories like Hubble and NuSTAR. 1 million miles away, at Sun-Earth Lagrange Point 1, Discover and SOHO watch solar activity, while at Lagrange Point 2, the James Webb Space Telescope and Euclid peer into the cosmic dawn. At the Moon, orbiters like LRO and Capstone pave the way for human exploration. Around Mars, MRO, MAVEN, and Mars Odyssey explore atmospheric history, while Juno orbits Jupiter's storms. At the outer boundary of the heliosphere, Voyager 1, Voyager 2, and New Horizons venture into true interstellar space, all bound together in humanity's shared quest for discovery. By surveying the entire sky across 102 colors of infrared light, SPHEREx bridges the deepest inquiries in astrophysics. It links the quantum origin of spacetime during the first split second of cosmic inflation to the structural formation of galaxies across billions of years. It charts the biogenic ices and organic dust grains that provide the chemical foundation for oceans and life on newly formed planets. Over its primary 25-month mission, completing 4 independent all-sky surveys, SPHEREx delivers a permanent, multi-dimensional atlas of creation. It stands as a testament to engineering innovation and human curiosity, revealing that even in the cold and silent dark, the universe is ablaze with the invisible light of discovery. If you enjoyed this deep dive into space exploration and mission architecture, hit the like button, subscribe, and leave a comment below.